so today we're going to look at the fundamental theorem of calculus. I'm going to start off by revisiting a thing I kind of talked about in the last video. What is a function defined by an integral? So last time I kind of briefly talked about it, kind of shows the problems. Here's a little bit more formal. If a function f is continuous on a closed interval, then g of x, which should be basically the antiderivative of this quantity right here, for all, this g of x is equal to this for all x in this interval. Then g is a function defined by an integral. The independent variable of the function is a limit of the integration. So let's take a look at what this kind of means and how this helps us out and how we do problems that are associated with it. So here's an example. I'm just going to walk you through this one. So g of x is equal to this expression right here, the integration from 0 to x of 2x dx, 2t dt. It is a function defined by an integral. We can calculate values of g by finding the area under the curve. So this is what I kind of talked about last time, very briefly, but here's a visual to help you see it. G at 0, g of x is 0, because by definition there will be a limit from 0 to 0. So, and it's one of those properties, if I have the limit from the same number to the same number, it's equal to 0. If I want to find out what, g of 1, then it's the integration from 0 to 1 of that function. And so I'm literally just finding the area under this curve between 0 and 1. And likewise, if I'm doing 2, then I'm going between 0 and 2. And I find the area of that triangle. From 3, it'd be the area of that triangle. So this is basically what's going on with these. And we need to talk about this because we're going to be looking at the fundamental theorem of calculus that comes in two parts. And here's part 1. And here it is. The fundamental theorem of calculus, the derivative part. If f is continuous on the closed interval, then g of x equals the integration from a to some function of x, h of x up here, of f of t dt for all x in this interval. Then the derivative of g equals what? It equals the function at that limit with the x in it times the derivative of that limit. Okay? And the bottom part is a constant, and the derivative of a constant would be 0. That's why there's no part down below. But we will expand this out to a more robust look in a little bit. So let's look at an example that I have to show you how this could be used, how this will be used. So I have an altitude of a helicopter. In feet is given by this function right here. H of t is equal to this right here. What is the rate of change of the helicopter's altitude when t equals 4? So what does that mean, rate of change? Well, it means the derivative. So what I'm asking you to do is tell me what is the derivative of this function at 4. So what is h prime? If this is h, what is h prime of t? What is that going to be? Okay, and it is literally the derivative of an integration literally just undoes each other, and it's this limit goes inside here and replaces the variable. So you take this t, you replace the variable inside. So whatever that is, replace the variable here. 64 minus 12 times t, and then times the derivative of the thing you plugged in. Since this is a t, the derivative of t with respect to t is 1. So h prime of t is 64 minus 12 t. And so if I want to find h prime at 4, you just simply plug in the 4. And you get 16. And it's a derivative. This is the altitude of the helicopter. So if I take the derivative, then it's going to be in feet per second, the rate of change. And there you go. When does the helicopter stop going up and start coming down? Well, what does that mean? How do I find that? Well, if it's going to stop, that means the rate of change or the velocity or however you want to look at it is 0. So this is the rate of h prime is the rate of change. Right here, that is the rate of change. And so then we're asking really when is h prime of t, which is 64 minus 12t, when is that equal to 0? And so then you can solve this out and you find out that t is equal to 16 over 3. And that would be in seconds. Okay, let's look at another example right here. If f is defined as this, write an equation for the tangent line to the graph of f of x at x equals -2. So I need two things here. If I'm going to write an equation of a line, I need a point and I need a slope. The slope would be f prime, and the point has to be the value of the function at -2. So I need to find f of -2. Well, then if I plug that in, it's going to be 3 plus the integration from -2 to -2 of the sine of pi t squared over 8 dt. And this is equal to 3 plus 0 because I'm integrating from the lower and the upper limit the same. That means this whole quantity is going to be 0. And so there's my point, -2, 3. I got to find my slope. My slope is based off of f prime. What is f prime going to be? Well, it's going to be the derivative of a constant, which is 0. And then I take the derivative of this quantity right here. And because this is a number down here, the derivative of that's going to be 0. So I take that number, that letter, and replace that letter with it. So this is going to be the sine of pi x squared over 8. So I just replace the variable with whatever that is up there. So if this was an x squared, I'm going to replace this t with an x squared. So just remember that you're replacing it. And then times the derivative of that. The derivative of that is 1. So there is my f prime, the sine of pi x squared over 8. Okay? And I need to do what? I need to find this slope at -2. So we plug in -2. We get the sine of pi, -2 squared over 8. That's going to be a 4. That's going to make this a 1/2. So now I have the sine of pi over 2, and the sine of pi over 2 is 1. So now I have my point, I have my slope, and so I just simply write my tangent line equation. Y minus 3, 1 times x minus a -2. So you can write it like that, which is what I recommend. If you have to compare, you just move the 3 over here and you get x plus 5. So any one of these two formats is fine, but that's how you do it. Let's take a look at another one. Okay. In this example right here, I'm taking just another different look. I'm taking the derivative of this quantity right here. Okay. So this is invoking the fundamental theorem of calculus. I'm going to take the derivative. This is a constant down here, so that's going to be 0. But the derivative of this is that quantity right there, that function, h of x, based off of the rule, that right there goes and replaces the t in here. So this is going to be the cosine of e to the x squared. But I have to times it by the derivative of that, the thing I plugged in. The derivative of x squared is 2x. And so this becomes our derivative. 2 times x times the cosine of e to the x squared. And that's our derivative. All right, let's look at another example I have down here. Same process again. We're going to take this and find the derivative of this quantity right here. So again, you simply take that expression there. This is a number, so the derivative of that's going to be 0. Take that quantity and plug it in here. So I'm going to get the natural log of 2x cubed plus 1. Okay, times the derivative of that, which which is a 2. So this expression right here is going to be 2 times the natural log of, and then cube all this, 8x cubed plus 1. And that should be our final answer. Okay? Let's see if I have another example here. So this one's a little bit different because this time there is an expression on both parts. So how does this work? Okay? Well, this is the long way around it. I'm going to show you this, and then I'll show you the easier way that we're going to look at it. And it kind of ties into the second part of the fundamental theorem of calculus. But let's take a look. So because our rule says we had to have a number in the lower spot down here, I can split this using our properties. This becomes the derivative with respect to x of, and then I can choose any number I want in the interval or domain of what we're talking about, which is basically, in this case, all real numbers. And so I'm going to choose a very simple number. I'm just going to choose 0. And I'm going to use that separating aspect for integrations, that property. So I'm going to write this as 2x to 0 of f of t dt. And then to this, I'm going to add the integration from 0 to the sine of x of f of t dt. Okay? And then to change this so it looks like it's like we had it in our rule, this becomes a derivative of, with respect to x, of a negative 0 to 2x f of t dt plus this dt. Okay? And so now that I have it in this fashion, now I can take and use the fundamental theorem of calculus. This negative is going to be right there. The derivative of this quantity right here is going to be f of 2x, where I plug that in for the t, times the derivative of 2x, which is a 2, plus f of the sine of x times the derivative of the sine, which is the cosine of x. And so that right there would be the derivative of that expression. Now, let me just go show you the fundamental theorem of calculus, and I'll show you this example here in just a second. I want to show you this first because it makes it a little bit easier to do what I just showed you. Here's the second part, the integral part. If I have a definite integration between a and b of a function, then this integration, when I work this out, and I kind of hinted towards this in the other ones too, in the last video, the antiderivative of this is g. Okay, g is an antiderivative of f. Then this is equal to g at the upper limit minus g at the lower limit. So if g prime is this in here, then it's the same thing. It's because f is g prime. And it's just take the integration of this, you get g at the upper limit minus g at the lower limit. Okay? So with that being said, let's go ahead and take a look at this example. And I'll show you how that works here. Because here's h, and I want to find the derivative at 1, but I'm going to find the derivative first. So I'm taking the derivative of this. This is the antiderivative of that quantity right there. And so when I take the derivative, that's why this all drops out. So this is g. Okay. When I take the derivative of this, h prime of x, that's what I'm looking for. And I'm going to do that upper minus the lower here. Okay. And so what's going to happen here is I'm going to take the upper part, okay, plug it in for t. So I'm going to get the square root of 16 minus x to the third squared times the derivative of that, 3x squared. It's the upper limit minus, now the lower limit. So I'm going to take that quantity and plug it in. 16 minus 3x squared squared times its derivative, which is going to be 6x. So that's what we get there using both fundamental theorems of calculus at the same time. And then if I want to find h prime at 1, so then I'm just going to plug 1 in for all this stuff. And so you just simply get 16 minus 1 to the 6th power is still 1 times 3 times 1 minus 16 minus, this is going to be 1, so this is going to be 3 squared, which is 9. Okay. And then times 6. Okay. And so what I end up with is over here is a what? The square root of 15 times 3 minus 6 times the square root of 7. And so that would be our answer there. Okay? So the fundamental theorem of calculus that I showed you allows us not only to do this, but it allows us to find and evaluate this expression when I know the antiderivative. Okay? And I showed you again a real quick example last time in the last video, but here it is in more detail. So now we have this as full blown. We have the fundamental theorem of calculus. We're ready to go. And so I want to integrate this, so I have to find the integration of the cosine. Okay? So the integration of the cosine is the sine of t. Okay? Now we're not going to put a plus constant because that would be for indefinite. This is definite. Okay? So the sine of t, and this is how we usually do it. We take the antiderivative, and then we evaluate it. This line means evaluate from 0 to pi over 2. So what we're doing now is we're getting prepared to do the fundamental theorem of calculus, which is simply the upper limit minus the lower limit. And I do recommend parentheses when appropriate, minus the sign at the lower limit, and then work this out. The sign of 0 is 0, this is 1, and your answer is 1. So here's another example. We got to find the antiderivative of this. So focus on that first. This is going to be equal to 3 times raised to the power 1 divided by the raised exponent, evaluated from 1 to 4. So this then, when we clean this up, is simply just going to be x to the third, evaluated from 1 to 4. So it's the upper limit minus the lower limit. Excuse me, that was a 3. And then you work this out and you get 63. Okay, so these are your fundamental theorems of calculus. Let's look at a graphical approach to this so you can see how this does in a graphical sense. Let's look at that example. So here I'm looking at this. What is the integration from 1 to 3 of f prime dx? So what does this mean? This is an antiderivative, right? So I'm asking, what is an antiderivative of f prime? Okay, well, the antiderivative of f prime would be f. The antiderivative of f prime is f. So I'm integrating a derivative, so this must be equal to, I'll just do it right here, f of x evaluated from 1 to 3. That's what that means. Well, upper minus lower, then this must be f of 3 minus f of 1. And what do I have a picture of? A picture of f. Do I have f at 3? Do I have the value of the function at 3? I sure do. 6 and 2 and 4. So remember, this is the antiderivative of whatever that is. Since that's a derivative, its antiderivative would be f. In a table format, f prime is continuous on a closed interval. What is the value of this? So once again, the antiderivative of f prime is f. So this is going to be f of x evaluated from -4 to -1, or f of -1 minus f of -4. And then we can use our table to find those values. here's -1. F at that point is a -1.5. And then F at -4, excuse me, F at -4 is 0.75. And then you work that out and you get a -2.25. All right, here's another look that will be asking the same kind of a question. So you just got to think about it a little bit before you jump into this. Look at the words they're using and put it into a symbol notation, or if that helps you out with this. If g of x, capital G of x, is an antiderivative of this, so what does that mean? If this is an antiderivative of that, then g prime of x must equal f of x. Okay? So, what is the integration from 2 to 4 of f of t dt? Since f equals that, then I'm integrating from 2 to 4 g prime of t dt. And that gets this integration of a derivative in place, visible, so you can use the fundamental theorem of calculus, which says this is simply going to be the antiderivative of g prime is g, and it's going to be f of g, I'm sorry, g at 4 minus g at 2. And they gave us these values up here in some sense. So we know that this over here is going to be, excuse me, let's stop for a minute. I'm looking for g of 4. So this is a little bit different. But what I have going on here is I have an equation that has that stuff in there. So this I know is -7. So I know that. But I can move stuff around here and solve for g at 4. If I add this quantity to this over here, I get g of 4 is equal to g of 2 plus the integration from 2 to 4 of f of t dt. And so this is equal to -7. And this integration can be just stay, and we found a value for g of 4 like that. So if I know what that is, if I have the ways to find what that is, then I can go ahead and figure it all out. If I had like a graph or something like that. But that is the value of g of 4, and this is how I can find these values. They ask this kind of question quite often, so be aware that it's using the fundamental theorem of calculus to find one of those numbers if you don't have that. This is a very good, important one. So much so I probably just, start so you understand that this is a very important example to understand what's going on in these cases and to recognize it when it does occur. Okay, and it's about the fundamental theorem of calculus, recognizing that the antiderivative of g prime is g, and I'm looking for one of the g's, which is from the fundamental theorem of calculus, and that helps you find all that. Here's another example down here. The derivative of function h is this. So what does that mean? Okay, I want to find this expression, but what does that first sentence mean? The derivative of a function h is that. Well, I just told you what h prime was. This is h prime. Okay, so with that, now I want to find this expression right here. So I'm literally doing what? The integration from 2 to 3 of all that I'm looking for is simply asking you to find from 2 to 3 of h prime. And there it is again. I'm integrating a derivative. So the fundamental theorem kicks in. The antiderivative of this is h. Okay, so I'll have h of 3 minus h of 2. Okay, and if I had some way to figure out what these values are, I can. But there it is. That is what that expression looks like. It is that, whatever the antiderivative is of that. you can use a calculator or whatever the case may be to figure this out, or later on techniques for help us integrating this out, which we don't know yet. We can actually continue this process out, but that's pretty much all it is. So the fundamental theorem of calculus has two parts. They mainly are talking about right here, you have the integration of a derivative or the derivative of an integration. I take the derivative of an integration, okay, is one of these are functions, expressions, and it's the same thing. Take that, plug it in, take the derivative of the thing you plugged in. And then the other one is this stuff right here, where I'm integrating, find the antiderivative, and evaluate it from the upper limit minus the lower limit. That's the second half. So these two things you're going to use quite often and constantly in upcoming stuff for the rest of the year, basically. So we want to make sure we understand this one. It is a fundamental theorem of calculus. And so we'll do more questions together, and that ends this video.